One last thing I wanted to cover before I talk about how to sort of what you should be talking about in an eye tracking paper and this is something which is not calculated in Data Viewer, but is kind of a useful thing to describe the variability of your eye movements. So this method comes from the world of clinical ophthalmology. So what we often do in ophthalmology is we get people to look at a single fixation cross, and we describe the scatter or variability of the eye movements around that cross. And traditionally, this is calculated by something called the bivariate contour ellipse area, or for the rest of today, the BCEA. So one of the reasons why this is a very, very popular way of describing the variability of eye movements in the clinical world is it's something you can actually calculate in Excel. You don't need a fancy stats package or R or MATLAB, and you don't have the right programs. It's a very quick and easy formula you can calculate in Excel. So this is actually in the Dropbox in the software folder, and this is just an example of how you could calculate this formula. So there is a paper online in the papers which explains BCA in more detail, but this is actually how you would do it. So in the left columns, I just have data based on X position and Y position. This can either be based on fixation location, or it could be based on samples, an actual sample to sample X and Y location. It doesn't matter. It just depends on how you want to capture the variability of the eye movement, either on a sample basis or based on a fixation basis. And what I've just done here is I've just plotted this as a scatter plot. So I've got 100 data points that are all kind of scattered around someone looking at the center of a screen. So you can see they're kind of all over the place. Well, the bivariate contour ellipse area is a formula it calculates a circle which encompasses 68% of the data points. What it does is it basically looks at the variance in X, the variance of Y. There's a Pearson point correlation between the two, and then you can put it into this formula here. And again, there's more details in the formula there, and it gives you the area inside that ellipse. And it gives you in degrees. So in this case here, the scatter, which is contained within that ellipse, which covers 68% of my data, is actually contained in an area which is 5.3 degrees squared in size. What's nice about that then is you now have a measure which you can quantify that spread. So instead of saying it's highly spread versus narrowly spread, you actually have a hard number that you can put into SPSS or your stats package of choice to describe the variability of eye movements. This is one way of doing it. In fact, the paper which I put online gives you another way of calculating that area. It's something called the within isoline area. Basically what it is it takes a heat map, takes a slice through the heat map which captures 68% of the area and the variance of the eye movements, and then reports that as a total area. The bivariate contour ellipse area is very good if you want a very crude measure of spread. Very easy to calculate in Excel. The within isoline area is a little bit more complicated. For that, you need to have R or MATLAB to calculate. The advantage of the within isoline area, though, is you don't have to assume that all the data points are clustered around one point. You could actually have several points on an image. So I just wanted to highlight that if you did want to find some quick way of describing the variability of your eye movements, then this is a very simple way in which you can calculate this in Excel. There's a long history in the clinical world of using this, going back about 20 years now. It's very simple, and it's a good, easy number, just to give you a number then to say how similar or spread are the eye movements across participants or between groups. So say, for example, if I go back to my cat video, the eye movements for the females were quite narrow. The eye movements for the males were quite spread because some were looking at cats, some of them were looking at the woman. And so that, one way of describing that pattern would be to calculate the bivariate contour ellipse and use that to describe the variance of the data. So I just wanted to highlight that, and again, there's a paper explaining this in more detail in the Dropbox, and in the software in the Dropbox, I just put this little example together just to show you how you can actually calculate those values in Excel, which are talked about in the paper. Again, the reason it's popular, the bivariate contour ellipse area, is it is something you can just do in Excel. No fancy math involved. It's just, the standard deviation of one, standard deviation the other, the correlation, and then throwing them together with this formula. Okay, so good. So what I want to talk about for the rest of today is things to keep in mind when you're reporting eye tracking data. Now, there are no standardized rules across all journals or even within a journal. Even in the Journal of Eye Movement Research, there is a lot of variability in how eye tracking studies are reported. What I've tried to do today is to go through and pull out what are good practices. What are things which, when I review eye tracking papers, what do I like to see? And likewise, when I write eye tracking based papers, these are things I keep in mind to make sure that that goes into the text. And I'm also going to explain why are they important to report. The very first thing, and this actually comes from the world of vision science, is that you have to describe everything about your setup. So the students in my lab know we have this basically the standard text that we copy and paste into pretty much every paper just because it describes the configuration, the actual geometry of our testing setup, and also the stimuli. So when you're doing eye tracking, you have to make sure you report information about the distance between the participant and the eye tracker. That's going to be important because we need that to calculate the degrees of visual angle. The size of the stimuli, again, you want to report those in degrees of visual angle, and you'll also want to report not only the size of the stimulus, but the actual size of the display area, the actual monitor. So how do you go about calculating degrees of visual angle? At school, you guys all learnt about sines and cosines and tangents, and you thought, when would I ever use this in my life? Guess what? This is actually one of those situations where it actually does help. Because what we're actually going to do is we're going to use tan to actually calculate the visual angle. So, calculating it is actually very easy. It's 2 times a tan, the inverse tan, of the size of the object divided by 2 over the distance between the screen and the participant. Okay, and that will actually give us the size in degrees of visual angle of the image on the retina, or the size of the image on the screen. But basically, that's what we're trying to get, is getting that retinal size. So a tan is the arc tangent. So most calculators would have this as tan minus 1. If you're doing this in Excel, Excel has a tan, MATLAB has a tan, R has a tan. Like I said, most of the time we would report this in degrees of visual angle. If you're dealing with very small eye movements or small stimulus sizes, then you may want to start converting, basically anything below 1 degree, you may want to start reporting it in terms of arc minutes. So 60 arc minutes equal 1 visual degree. So instead of talking about 0.33 of a degree, you could talk about 20 arc minutes. It's a whole number. People deal better with whole numbers.
How do you calculate the object size?
Well, I'll come to that in a second. Okay, so yeah, you can talk about this arc minute. Now, if you're dealing with very, very small sizes, then you can actually talk about things in terms of arc seconds. So each arc minute equates to 60 arc seconds. So basically, one arc minute is 1/60th. Each arc second is 1/60th of an arc minute. So again, these are ways of giving you other ways of describing size of stimuli, which doesn't necessarily negate, you don't want to have lots of decimal places with zeros behind. So it's another way of reporting. So sometimes you'll see, especially when you're dealing with very small eye movements, so drift, tremor, microsaccades, most of those journal articles will talk about the size of the eye movements in terms of arc minutes and arc seconds. So if you do see that in a journal, just be aware that those come from 60 arc seconds equal an arc minute, 60 arc minutes equal 1 degree.
Is this for the images as well as video?
Yes. Yeah, we're talking about very, very small eye movements here. So, arc seconds are kind of hair size of eye movements, like the width of the hair. So incredibly small. Most eye trackers will only record, they'll record degrees. Some of them will record down to arc minutes, most of them will not. And very few will record down to the arc second level of accuracy. So the two ones which are on the market are the dual Purkinje eye tracker, that's sort of monstrosity of a machine, and the iLink. Both of those will actually work down to arc second resolution. If you have a Tobii, in theory it can report at the arc minute level. You're really talking about degrees, though. And I'll show you why in a bit, why I say that. So here's just a quick example. So imagine I have a cat on the screen. It's 50 centimeters tall, and I'm viewing it from a distance of 1 meter, so 100 centimeters. So to work out that cat as a size on the back of the retina, so my angle back here, it's 2 times a tan, the object size divided by 2 divided by the object distance. So if I do that and plug those numbers in, the size in degrees on the back of the eye is about 28 degrees. Okay, so that's how, it's not complex math. It's using math you all learned at high school. So it's not you can plug these numbers in an Excel file, but it's really important because reviewers will want to see the size of your stimuli. They don't care about it in pixels. They don't care about it in centimeters. All they will care about it is in terms of degrees of visual angle. I'll show you in a second. So just in terms of how you might report this in a method section, so something like stimuli were presented at 43 centimeters, flat panel monitor, the viewing distance of 60 centimeters, with the stimulus being 18.5 by 12.4 centimeters, which subtend or equate to 17.5 by 11.8 degrees of visual angle. That would be a sort of a sentence that you will find in just about every good eye tracking paper. When it comes to measuring the size of stimuli, along with having a little light pen in your pocket, the other thing which all good people will have is a tape measure. Measure everything down to the millimeter. When it comes to the screen size, do not report the manufacturer's specification. Why? Manufacturers will actually tell you the screen size is the actual diagonal frame of the entire front face of the monitor. Whether it's an LCD, a fancy flat panel TV, or whatever, they'll tell you the physical diameter of the entire box. What you're more interested in is actually the viewable angle. So what you can do is take your tape measure, put it up against the corner of one screen where the screen ends. So before it goes on the plastic, put tape measure there, measure the diagonal to down here. Likewise, the height and the width. Physically measure it with a tape measure. Don't trust their specifications. When it comes to distance from the screen to the person, get someone to sit in your in your chin rest. Get them to look at the screen. Take a tape measure from just where their eye is and measure it to the screen. How far is that away in centimeters and millimeters? Okay. If you're using the eye link, there's an easy way of doing this. So on the side of the eye link, where you kind of adjust the knobs for raising the chin rest up and down, the very center of it, there's kind of like a knob wheel, has a circle. That circle actually is perfectly lined up with where your eyes would actually rest on the chin rest. If your head is in the forehead rest, your chin is in the chin rest, that circle aligns up perfectly to where the eyes will be. So you can just take your tape measure from that point and measure it to the screen. Okay? Measure everything. Trust no one. Okay? Especially if you've had cleaners come in the room, you've had undergraduates who may be playing around with the equipment and moving things, not realizing that they shouldn't be moving this. I hate to say this, I've visited labs before where they've said, well, we've got this eye tracker, but we can't get it to work. Like, what do you mean you can't get it to work? It's like, sometimes it works, sometimes it doesn't work. It's like, well, okay, fine. What do you do? Like, show me what you're doing. They'll sit there and they'll move the screen in and out. They'll move the position of the eye tracker. They'll move the chin rest between participants. And I'm like, well, that's your answer. You're moving this because these eye trackers need to know that information down to the millimeter. In fact, most of the eye trackers, you actually have to enter that information into the computer. You have to tell it the screen size in number of pixels, the physical dimension size, the distance, in order for it to calculate saccade amplitude in degrees. So for example, the eye link upstairs has a very, very detailed file explaining the physical configuration of every parameter you could imagine, and then some, between where the person is and the screen and the chin rest. So it's critical that you don't play around with those. Measure them, report them, don't touch them. If you think someone's touched it, go back in there and remeasure everything. Double check before you go on. Okay. Second, make sure you describe the properties of your actual eye tracking system. Not all eye tracking systems are the same. There are differences between eye trackers in terms of the quality of the eye movements, in terms of that they record, the sample rate, the size of which they're actually able to sort of classify their eye movements. All of this is different from one eye tracker to the next. Even an eye tracker, from the same company. It's a different model. They have very different characteristics. So make sure you report that inside your article. So for example, make sure you say, what is the sampling rate of your eye tracker? Some eye trackers don't have they only record at one sample rate. That is usually 60 hertz for most typical eye trackers. For like the eye link upstairs, we can sample from 250 hertz up to 2000 hertz. So make sure, even though you've got an eye link, make sure you say, this is the sample rate that we were recording under. I'll show you why these are all important in a minute. Make sure you report the accuracy and precision of your eye tracker. Either the manufacturer's specs, that's good. Better, the ones that you measure for your individual piece of equipment. Talk about how head movements are dealt with. Again, this is the reason why we use chin rests. We don't have to have head movements. If you don't use a chin rest, you have to talk about how your eye tracker deals with head movement and how it compensates for it. How quickly does it recover from a head movement? That's the other thing. So if you actually it loses data, either because someone moves, someone blinks, how long does it take it to reacquire and accurately give you data? Also, how does your system deal with lost data? So either lost because of an eye movement or data which is just, you've got gaps in your results file. How does the analysis software deal with that? Okay, I talked about sample rate. Sample rate is probably the most critical thing to think about when you're buying an eye tracker, because it's actually going to affect the quality of data you get off. So eye tracking really goes between, there are some 30 hertz eye trackers out there. Like I said, most common are 60 hertz, up to 2000 hertz. So just to show you why sample rate matters, here I have a theoretical fixation in red. So it's starting at this time point over here, and it's ending at this time point over here. What I've got here is I've got 4 different eye trackers, each of which is sampling at a different resolution. So let's start off with the 50 hertz eye tracker. This would be our kind of budget eye tracker. Okay, so it is only sampling at 50 hertz. What that means is, because this eye fixation starts and it's between sample locations, it's not going to detect that fixation until much later on. So it's only at this time point here is actually starting to actually register that there is a fixation currently going on. So I don't have information about this part of the fixation. If you go to the end, again here, this fixation in reality ends between 2 samples. As a consequence, the eye tracker will keep on saying that it's in fixation until the next sample point. And so you can see there's going to be large periods of time where I'm not getting a good, accurate representation of my data, of the fixation. As you start increasing the sample rate of the eye tracker, that ability to correctly capture the onset of the fixation gets better. So by the time you're in the sort of 500 hertz to 1000 hertz range, you're really getting a good, you're quite accurately capturing the onset of the fixation and the offset of the fixation. So what this shows is that faster sample rates tend to be much better eye trackers. They also tend to be much more expensive eye trackers. So a 50 hertz eye tracker, until recently, you could pick up for $100. The company who actually produced that just were bought by Oculus Rift, and they've stopped making those. But if you can find they're called the iTribe. Very good little eye trackers. They do 60 hertz binocular eye movements. Good low-cost eye tracking. You can still pick them up on eBay and places like this, but they're gone. But even sort of, there are a couple of $2,000-$3,000 eye trackers out there, all of which are around about the 60 hertz eye tracking. So again, those are good. They're good for telling us where you are on the screen. You can kind of do some fixation data analysis with them in terms of you're going to get something which captures a fixation. It's just not going to be very accurate. So if you're looking for big differences in fixation duration, it's fine. If you're trying to show smaller, subtle differences, say, for example, in reading research, a 60 hertz eye tracker will not do. Obviously, as you start going up in sample rate, you're going to get to more expensive eye trackers. So if you're talking about a 1000 hertz eye tracker, you're looking at spending over $40,000 on one of those eye trackers. So again, depending on the type of eye tracking study you want, if you want to just know where people are looking, a 60 hertz eye tracker is fine. If you're looking for big differences in fixation durations, a 60 hertz eye tracker is fine. If you want to start looking at more subtle characteristics, you need a higher sample rate eye tracker. But again, make sure you report that. What is the sample rate of your eye tracker? Eye tracking you should also report the accuracy and precision of your eye tracker. The first is very easy to get because companies all love saying how accurate their eye tracker is. Precision is different. At the moment, very few companies actually report their precision of eye tracking, mostly because they're terrible in most eye trackers. So just to tell you what the difference between accuracy and precision actually is. Accuracy is the average distance between the true gaze position and where you were recording from. Precision is our ability to reproduce that measurement. To show you graphically, what I've got here I've got a target at the center. The cross represents really where the person is looking. The red circle reflects where the eye tracker thinks that the eye is looking. So just to show you how accuracy and precision interact, on the left here, what I have low accuracy. So you can see the eye movements are all clustered quite closely together, but nowhere near where my actual participant is looking. But they're nicely closely clustered, so the precision, the sample reproducibility is very good. Here we have what is actually most eye trackers. High accuracy with low precision. So you can see, overall, the eye tracker is getting it that they're looking near the center of a target. But you can see the sample-to-sample reproducibility is all over the place. Here, this is what we really want to have. We want to have high accuracy and high precision. So we want all the eye movements to be where the person's looking, and we want them all closely clustered together. So when eye tracking companies report accuracy, and they all do this, they will all say, oh, our eye tracker is accurate within half a degree. What they're talking about is accuracy. What you really want to know as well is not just accuracy, you want to know the precision, because precision is the difference between this and this. Precision, if it is reported by an eye tracking company, will be reported as the root mean square, or RMS, angular distance. Just to give you what that means, 0.01 degrees RMS actually equates to a noise of your sampling of 0.0001 degree. Okay, iLink, this is one of the few companies who actually do report both the accuracy and precision of their eye tracker. If they do not report it, you're going to have to go and find out what it is. So the easiest way to do this is to go back and print off a black circle. Put that up where the person's eye should be, put up a fixation point at the center of the screen, and record the eye movements for a period of time. Okay? That black circle is not moving. Okay? So whatever the variability in eye movements as your data is being recorded by your eye tracker, that tells you the precision of your eye tracker. If your eye tracker is good, all those numbers should be identical. If there is any kind of sample-to-sample variability in precision, that could be coming from the video sensor, fluctuations from the infrared emitters, through to how the algorithm is parsing the eye movements and fixation locations, that will come up as more variations in your recording. So you can sit there, you can calculate the accuracy of your eye tracker, you can calculate the precision of your eye tracker. And if you're really good, you should ignore the manufacturer's specifications and do that yourself on your eye tracker. You don't need to do this once. Just get an idea of how good your eye tracker really is. Because again, every eye tracker, although they're manufactured, there are small, subtle differences every time a piece of machinery is made. There may be differences in how good your eye tracker is. You may be even more accurate, or you may be likely less accurate than what they report. Just to give you, so this is actually Kenneth Holmquist has done. He's like Mr. Eye Tracking methodology. Here is, he actually went out and actually calculated the precision on a number of different eye trackers on the market. Okay, so this is actually, so this starts off with an iTribe, which is, remember, it's the cheapest eye tracker you can buy, and goes through to a dual Purkinje and the iLink system, which are probably the most, which are considered to be the most accurate and the most expensive eye trackers on the market. So what you have here is, here you actually have the RMS precision across these different devices. And these were actually recorded, he did these assessments multiple times to get the sort of these box plots. So let's say, for example, here we've got the Tobii TX T60. This is a very, very common eye tracker, especially in Europe. So you can see its accuracy and precision is actually kind of similar to an iTribe. The difference is the iTribe costs you $100. A Tobii costs $35,000. Okay. Now you get over here. These ones which are marked red are SMI eye trackers. This is another company. They do, they're performing fairly good. Then you start getting over to the iLink, and you can start seeing, this is where you start seeing, first of all, the precision starts dropping, but also the variance of the precision also drops a lot as well. So you start getting quite accurate eye tracking down from the iLink. The dual Purkinje imaging system is still the best on the market, but it's kind of bulky, big. It's expensive, and it's very difficult to set up, and you usually have to bite down on a bite bar when you're actually using it. So not just using a chin rest, but a bite bar. So it's not the most comfortable eye tracker to use. It still is used by some researchers, but mostly now, if you're doing hardcore eye tracking, most people have gone over to using iLinks to do this. And that's the reason why. So always make sure you look at the accuracy and the precision of your eye tracker, and you make sure you report either the manufacturer's specs, or if you've done your own homework, report your own system's specifications. When I was talking about dealing with head movement, this is important because not all parts of the eye tracker are equally accurate. And we talked about this when we did the hands-on upstairs. We said that you tend to have very good accuracy near the center of the screen, and then as you start getting more to the extremes, you start getting poorer accuracy. Well, that's true if the person's head is stationary. It gets a lot worse when the person's head is moving. So as the person's head is moving, that point of accuracy is going to shift with them. So make sure you talk about or look at seeing how good your accuracy is in your eye tracker as you move the person. Just to show you what this would look like on an iLink. So this is actually something which we put together a few years ago. Here we have looking at viewing distance. So all I did is got people to move the head backwards from the screen and record the precision. In fact, we were actually doing this with a black dot. We recorded the precision, the RMS precision of our eye tracker when we did this. So what you can see is it kind of stays stable over a range here. After about 70 centimeters, as I start moving away, the precision of my eye tracking goes way off. And that's why iLink recommend that you record between 60 and 70 centimeters away from the screen. You can see here, that's because you're far enough away from the screen that people are not going to squint too much. If they're too close, they're going to squint. At the same time, you're getting the most accurate precision. After about 70 centimeters, that's when you start seeing this increase in error of your eye tracker. Related to this, look what happens. So you can take that eye, cover it with your hand, bring it back on. That's like simulating a head movement. How long does it take for the eye tracker to reacquire the data? If you can time this, so one way you can time this is if you can actually put an infrared light behind the black circle, and have that flip on and off and have that hooked up to an oscilloscope, you could actually, there's a complex way of doing this. If anyone wants to, I can show them how this is done upstairs. There's a way of doing this. It takes about 5 minutes to measure, but then it looks and it sees how long it takes your eye tracker to reacquire data based on a head movement. Again, you can do this very, very simply as well by just video recording a person from behind looking at the screen. So basically, you have them in calibration mode. You get them to move off the screen, move back on. You play the video back at a slower rate, and you see how many frames it takes for the eye to reappear. That would give you a rough idea of how long it takes your eye tracker to reacquire eye movement data. So again, just how you would talk about this. This is actually from a paper. Eye tracker monitor has cameras embedded to record eye movement reflection of infrared light from a cornea relative to the pupil at a frequency of 50 hertz. The average accuracy of this eye tracking system is in the range of 0.5 to 1 degree, which equates to half a centimeter to 1 centimeter error on the screen at a viewing distance of 60 centimeters. When both eyes could not be measured, either due to head movement or head position, data from the other eye was used to determine eye coordinates. Again, this is where I talked about how do you deal with missing information. So if you are missing data, so if you're recording binocularly, you lose one eye, how are you dealing with the data in that situation? Whatever you choose, make sure you talk about it. Temporal accuracy error is about 1 degree in case of head movements, and with a 100 millisecond recovery time. Yeah.
So when we do calibration upstairs, and we try first with the 2 eyes, and then we start noticing that one eye is just not behaving,
Yeah.
something's going on. We choose the other eye.
Mm-hmm.
That's when we go into talking about data from the other eye.
Yeah, you could. You talk about in terms of how do you make that judgment. So in this case here, we binocularly calibrate. The eye which has the most accuracy is the one we record from. As long as you're open about it and put it, no one's going to penalize you. As long as you're open about how you're dealing with recording your data, that's important.
And how about when, for example, in simple trials, which is what I'm going through right now, it'll work, for example, on one eye, one trial, and then they come back and they do a second trial that works on the other eye.
Then you have to talk about exactly how many of those conditions did you switch over.
Okay.
Talking about calibration, make sure you describe the calibration process in full. How many calibration points did you put up? Okay. Are these, if you're using the standard default locations based off of the system, that's usually fine because they're usually published online with your eye tracking company. If they are not, if you're using custom locations for your fixation position, calibration positions, report where those were. What was fixated? Was it a fixation target? Was it a little dancing bunny? Whatever it is, make sure you describe the characteristics of your calibration target. How are you judging the fixation of the stimulus at each location? So in particular, was this an automatic algorithm? So on some eye trackers, what will happen is you look at the fixation calibration target, they will sample for a period of time, and then it will move on. Was this manually entered in? So did you get the person to look at the dot and then press spacebar when they were correspondingly looking at the dot? Again, describe how that process works. Automatic and manual, as we explained when we had the hands-on session, can give you slightly different accuracies in calibration. Automatic tends to be faster, a little less accurate. Manual tends to take longer, but is more accurate. Again, most of the time, the eye tracker is storing all that information about known locations, and it's using those to interpret the movement of eye movements in an experimental procedure. Again, good calibration usually requires the participant to actually fixate the stimuli. So if you're dealing with babies, for example, don't use an automatic calibration. Make sure that, look at the actual video feed. Make sure they really are looking at the calibration point manually enter that information in. If you're dealing with older subjects, so adults, students, automatic's fine. Just make sure you kind of keep an eye on the actual video data to really make sure they are looking at the calibration target when they're supposed to. Some systems like the iLink will not let you advance on unless you actually are looking at the target. So say, for example, when we put a drift corrector up at the start of a trial, you actually have to look at that and press spacebar in order to go on to the following trial. And if you're not looking at the target, it'll flash red and it'll give you that burp sound, and it won't let you go on. Other eye trackers won't do that. Other eye trackers, they don't care if you're looking at the fixation target, it'll still go on. Again, if you are using custom locations, please make sure you report those locations. Make sure you report the size of your calibration target as well. So for some of you, when you were doing the experiment builder, you kind of got the feedback you're using a target that's way too big. That's because there's different locations where you could look. What you want to have is a fairly small target, preferably a target within a target, to really focus them down into looking at a single point. So the most common type of calibration point is a black circle with sort of a white circle in the middle. That's a good one. The other one is if you have a white circle, a black circle, a white circle, and a crosshair. That's the best because you've got multiple things drawing you to look at one single point on the screen. The more you can get them to look at that single point, the more accurate your eye tracking calibration is going to be. And again, make sure you also report whether it's automatic, manual, as in the participant is telling you when they're looking at the fixation point, or is it manual when you, the experimenter, are deeming that they're looking at the calibration target. So make sure you report how you're actually calibrating. Again, systems will vary in how they deal with missing data. So for example, some systems will have an eye blink filter built into them. What that will do in some systems is it will freeze the eye position at the moment of the blink. And so what will happen is the XY coordinates of your fixation eye position will remain the same during the blink. And when the eye opens, then it will relocate to the new location. Others will actually not record eye position at all during a blink. So make sure you talk about how you're dealing with that missing data. So especially blinks. Blinks are the big one. So is it, does the system freeze? Does it remove altogether? The other thing as well, like I said when we were looking at the real data, is that if you look just before a blink, look at how your eye tracker is, what's it doing to the eye tracking data just before a blink onsets. Some eye trackers will mark that as a saccade. Why? Because what happens in a blink is you're closing your eye, so the pupil is rapidly changing size, and so for some eye tracking algorithms, it's fooled into thinking that the actual eye movement is in the saccade and not actually that it's a blink. So have a look at the raw data, just see how it's parsing it. So good eye trackers will actually take a blink period and actually then also not only give you no eye tracking data around that blink, actually it gives you no eye tracking data 100 milliseconds before and after the blink as well. Because that way it makes sure you don't have any of these saccade artifacts that might be coming in and corrupting or influencing your data. Make sure you talk about how your eye movement data are actually processed. So most data from eye tracking is actually processed in a number of different ways, even before you get to see it. So for example, eye tracking data, when you look at the data viewer, often is not raw eye tracking data. What you're often looking at is how it's been processed into fixations and saccades. So sometimes the data are actually filtered to kind of smooth out some of the noise in the sampling data, even before you actually get to save it in the results file. So make sure you look, and when you're thinking about eye tracking, make sure you see what the eye tracker does. How the samples being dealt with. Are they being filtered online? Are they being parsed online? Because if so, it takes a few milliseconds before you have that information, so there's a delay in the eye tracking. Find out how it deals with the filtering. This is a little bit more tricky because some eye tracking companies won't tell you this. You can kind of piece it out from papers and methodological people who have done this already. So for example, are they applying some sort of smoothing algorithm to reduce noise in the data, and therefore that'll help calibration? Are they doing some sort of offline coding or offline filtering of your data? Again, it depends on the company. Some companies do this and don't tell you. Some companies do this and do tell you, and then other companies don't do filtering. Overall, filtering can have a lot of negative effects. So it's good, in fact, that it reduces the noise in your system, but at the same time, it does actually mask some of the smaller, finer eye movements, which may be important in your particular experiment. So again, if you can, try and find out if the eye tracker, how it's actually processing the data. So again, there's an example here. In this case here, they actually smooth their data themselves using a bilateral filtering algorithm. So this is very similar to the algorithm which I showed last time for pupillometry. So it takes the individual pupillometry and kind of smooths it out. Again, make sure you just report that. Anything you do to your data which could change it, just be honest, talk about it. Were the data reduced? Or how are you reducing the parameters of data, and what are the procedures that you did that? So like I said, eye tracking data is incredibly complex and data rich. There's a lot of information going on in an eye tracking study. And it produces a lot of data, sometimes too much data. So some people will simplify that. So make sure you define it. So if you're only looking at a particular window of time, so if you're using the interest period filter, you're only caring about the first second. Make sure you state you're only analyzing the eye movements from a certain period of time. What is that period of time? So for example, I would say we're only interested in interest period within 1 second on the onset of the stimulus. That's a simplification. If you are, when you're talking about fixation durations, some researchers will exclude fixations which are under 100 milliseconds. Some will also exclude fixations which are over 2 seconds. Why? Because most fixations are between sort of 250, 300 milliseconds and 1 second in duration. So if someone's looking way too long, they're probably bored. Likewise, if it's a very small fixation duration, maybe that's just an artifact. And so you'll often see that researchers will say we're only going to classify fixations between this period and this period. Again, if you're going to do that, that's fine. Just make sure you write down how you're classifying this. You can just report it as a percentage. You can just say, by doing this, we remove 2% of the data. Well, what you could do is say, okay, what are all the fixations? Okay, how many of them are below and above your value? That gives you how many would be removed, and then it's just a simple percentage. Fixation, distribution, trimming. For those of you who are cognitive psychologists, this basically is the same problem we've had with reaction time trimming, in that some people like it, some people don't. Some people see it as a fact of, well, data is data and you should explain it anyway. Others are, well, by trimming the distribution, it becomes a normal distribution, so I can run parametric analysis on it. There's no right or wrong way of doing it, but whatever you do, make sure you just talk about how you do it. So if you're including all the fixations, say that. If you're trimming, say that. Again, be honest. Again, make sure you provide the variables, anything that might be interesting. Just make sure you really talk about why you chose to do that and what was the process you did. And then, you could say how much of the data were removed using these processes, or how much do you still include. That's the other way you can do it. So for example, for fixations, and very few people actually do this, how are you defining a fixation? Okay? Very, very, very few eye tracking studies actually do this. I could define a fixation as a pause of eye movements for over 100 milliseconds within a 1 degree window. Or I could say, well, there's a fixation is defined as a pause in eye movements for 100 milliseconds within a 5 degree window. My fixation, that's going to change the number of fixations that I actually have. And so you should be again, if you're using the default, it's not so bad. But if you are using your own way of classifying a fixation, make sure you do that. And even in Data Viewer, you can go in there and look into preferences and see how are this, by default, how is Data Viewer configuring fixation duration. So by default, Data Viewer starts as 0 milliseconds. Pause, which is basically one sample. So you may want to change that parameter, and again, just report that. So for example, fixations were calculated by the mean XY position of consecutive data fall within a 30 pixel radius for 100 milliseconds. That could be in degrees as well. In fact, that should be in degrees. Just define how you define a fixation, how you define a saccade. Saccade was an eye movement over a certain distance with a certain velocity. That's usually the textbook definition of the saccade. Normally, it's an eye movement that exceeds 1 degree of visual angle and with a velocity of 100,000 degrees per second. Very fast. Saccades are fast. So something like that. And again, those are you can go into the parameter settings and see by default how you're actually analyzing it. If you change, again, that's fine. Make sure you define, say how it's changed. So again, that's just an example for saccades here. When you have an area of interest, make sure you report, in terms of fixation time, eye movement first, eye movement to that area of interest, or whatever variable you're interested in. So dwell time, percentage of time of the total trial time, whatever it is. Talk about how you drew those areas of interest. So were they hand-drawn? Were they predefined in terms of an area of pixels on the screen? Were they regular shaped? Were they oval, rectangular? Were they the same shape? Were they a different shape? Did they have the same area? Very, very few studies will do this. Even better, instead of, and it's a lot of information. If you can, and most eye trackers now let you do this, you could export your interest areas. So with all our interest areas we've been doing, if you right-click on it, you could say export interest area. That saves all of this information into a file, which then you could put up as a supplementary material with your journal article. That means that people can go in there and get all that information. So if they want to do a real replication of your study, they're going to have the same area of interest sizes. Otherwise, they're going to be drawing them themselves. They may have different sizes. As a consequence, their results may be different from yours. Okay. Remember that defining and saying those sizes. If you have a big area of interest versus a small area of interest, that's going to change your results. When you're drawing an area of interest, remember, don't draw closely around your object. Think about your accuracy of your eye tracking system. So if your system is accurate to 1/2 degree, make sure you have an idea of how you add 1/2 degree of size around each of your interest areas. Because that way you're going to really make sure you capture the eye movements on that area of interest. Again, don't make them too liberal or too conservative. Really you want to make sure that they actually are around your object, not that they're covering the whole screen or so tightly around the object that if they're not directly looking at it, that because of the accuracy of your system, then it's not really going to come up as measuring inside the area of interest. Again, you can define them in terms of specific pixels. I could go in a table. Much better, just export those area of interest files and just put them up as a supplementary material. That way, if someone really cares about this stuff, then they can always go and look at it themselves. Again, differences in looking time, proportion looking times can really only be understood if we know the sizes of the interest area. So make sure you define them and how you actually define them. So an example here would be each side of the rectangle was a distance of tending approximately 1.1 from the most protruding point of the image. The center of the screen was also delimited within the area of interest. For each infant, we calculated percentage of trials in which first looks were directed to a certain category area of interest. For example, first looks, and the average number of fixations within an area of interest per slide. So this would be some way of describing how you define those areas of interest around each object. Finally, again, when you're talking about inclusion or exclusion criteria, make sure you talk about that in your results. So were trials excluded when participants failed to look at the stimulus? Okay. This is something, again, not many studies will actually report. They'll exclude participants because of fussiness, but they never define why. So an easy way of saying this is, well, what you can actually do is draw one area of interest around your entire visible stimulus or your screen and say, if the person doesn't look at that for at least 90% of the viewing time, then they're fussy, therefore we throw them out. That's one way of really defining inclusion of a criteria. So if you've got someone who falls asleep during your experiment, is just randomly pushing buttons and they're kind of not looking at the screen, you then can, using this, you could very easily say, well, unless they're looking at the center, unless they're looking at the screen or the stimulus at least 90% of the time, whatever you define, then we exclude them. Again, if you do that, make sure you just talk about it in the start of your results section. For participants, are you going to look, if people are blinking the entire trial, for whatever reason, if you decide to exclude them, either based on behavioral data or eye tracking data, make sure you talk about why, the rationale as to why they were excluded, and make sure you actually put that down in the results section. Again, this is something which very few people actually do, but is really nice because it then tells us a little bit about the quality of the actual tracking. If I know that people are looking at the stimulus and doing the task, the eye movement data and the behavioral data have meaning. They're not looking at the doing the task. Is that data really any use? So yes, it's eye tracking data, but actually is it telling us anything useful? So that is sort of a set of 8 very quick and easy rules to follow when you're reporting eye tracking studies.